Welcome. I'm David Amos Brown, and this is a quick but good overview of the ABCAP operating system to support the alpha software on the SentientSync website and the Kickstarter campaign. The next video will show in action what is discussed here concerning the creation of AOS programs. We are looking at two graphics I prepared that shows the hierarchy of things in the AOS system. The AOS system at any given moment can be simply described as a set of users with unique names, running a set of computer applications on a set of machines with unique names connected to work together. One of those applications on all computers being the ABCAP operating system with a unique license number. AOS is a tree-structured system with a central library AOS machine at the root, retaining user, machine, and AOS license security information. Branch library AOS machines extend the secure network outward, allowing client computer AOS machines to connect to various branches for network traffic management. The entire AOS tree can be viewed as two parts: a networked machine tree and a computer application tree that continues the machine tree into each computer. The tree structure allows all information on the tree to have a unique address for global read access by all programs. Security settings can change that default access, and the tree structure can grow without end. Continuing up the hierarchy, computers are basically a set of software applications. All applications have user interfaces, or you couldn't run them, and all interfaces have software controls. On every interface, there is at least one control for receiving application input, and at least one control, maybe the same one, for showing application output. All interface controls have data values that govern their content, appearance, behavior, and status, CABs, on the interface. The total set of these governing data values for a control is called a driver. They are the values that drive the functionality and appearance of the control. Controls on an application interface either provide information to the programmer behind the interface or to the user in front of the interface. The names of controls on an interface are information to the user and provide clues as to what the application does. This is an application's visual design. At the top of the hierarchy is where all our work is centered. A software application's functional design is all the intelligence behind the application's user interface required to interpret user input requests and provide the output result information. Professionals call this the code behind. I call it the dungeon in traditional code, but that's not AOS. Algebraic expressions are the only means by which we tell the computer how to do something informational. The expressions are in essence our program, the informational things we tell the computer to do when informational things happen, conditions, in the program. Describing what functions to apply to what data in what order is the language of algebraic expressions or equations. The design of a program defines the expression's functions, data, and order. The operation of a program controls the time at which expressions evaluate. Enter the AOS trigger data type. In traditional coding, we type out all our expressions that later get interpreted by a compiler, which we won't even discuss and be grateful you don't need to know. Algebraic expressions in software are more powerful than mathematics because they can use any kind of defined function and work on any kind of defined data. That's informational freedom. And this is where AOS building and traditional coding part company. The major difference between AOS and other software development environments is the amount of effort required to complete an application and how we create it. There is nothing fundamentally different on an academic level between defining expressions in AOS and defining them in traditional coding. AOS programmers still apply the same set of academic functions like square root to the same data in their expressions and use repeat loops and conditional branches to control expression evaluations just like traditional coding. We just describe it to the computer differently and have less to do. The reason why AOS programmers have less work is because AOS controls have driver values or settings that span their entire range of functionality. Anything the user can do manually, a program can do through a driver value. For example, many controls have a header color driver value that can be expressed and therefore changed by the computer. In contemporary software, the code behind contains hundreds if not thousands of solution variables and their expressions required to manage the computer and your solution at the same time. In AOS, all the computer-related variables are gone, allowing us to build 20 AOS expressions that can do the work of 200 traditional code expressions. AOS is in essence a bubble of understanding around the programmer user. Inside, all the information can be academic, pertinent, and managed the way we learned in school in a straightforward manner. Outside is me, AOS, wrestling with the computer trying to get it to do what you asked me to do. Did I say that out loud? In the final analysis, a software application is simply a set of expression sequences, or programs, that respond to user actions, information requests, and show the user results. For instance, the user pushes a button, an expression sequence starts, and when it's completed, something on the user interface fulfills the user request or shows the status of the request in some manner. And so, our work building software in AOS is the same as in traditional coding and involves the following important process. 1. Define the application's purpose clearly. 2. Define the information sources and the information capabilities required to fulfill that purpose. 3. Define the application's interface to support the application's capabilities. 4. Define all the application states anticipated. For instance, startup mode, edit mode, idle mode. 5. Define the variables required to manage the states of the application. 6. Create the application interfaces, if there's more than one. 7. Create the variable expression sequences that respond to all possible user inputs in the defined application states.